In this video, we are going to be learning about the colligative properties of solutions. Colligative properties are properties of solutions that depend on the quantity of solute particles, not the identity of the solute. Examples include freezing point depression, boiling point elevation, and osmotic pressure. For example, a 1.5 mol calcium chloride solution will have the same freezing point as a 1.5 mol barium bromide solution, because both of these substances produce the same number of dissolved particles. The freezing point of a solution is lower than that of the pure solvent because the dissolved solute particles interfere with the intermolecular forces between solvent molecules, preventing them from organizing into a solid. As a result, a lower temperature is required to freeze the solution. Similarly, solute particles interfere with vaporization during boiling, so a higher temperature is required for molecules to enter into the gas phase. Therefore, solutions exhibit freezing point depression and boiling point elevation. In cold climates, roadways are salted in the winter in order to melt ice on the roadways, meaning the current external temperature is no longer cold enough to keep the solution a solid, resulting in melted ice. When we add salt to water when cooking, the boiling point increases. However, we are not adding enough salt to make a considerable difference. Adding salt to water for cooking is mostly for flavor enhancement. The magnitude of the freezing point or boiling point change depends on the molality of the solute, not its chemical identity. However, some substances ionize in solution, producing multiple particles. The number of particles depends on electrolyte strength. Strong electrolytes fully ionize, weak electrolytes partially ionize, and non-electrolytes do not ionize at all. The ionization factor, also called the Van't Hoff factor, given the symbol I, describes how many particles a solute produces in solution. Strong electrolytes fully dissociate. One solute particle can split into 2, 3, or more separate ions when dissolved. The ionization factor for a strong electrolyte equals the number of ions formed. Weak electrolytes partially ionize, giving an ionization factor between 1 and 2. Non-electrolytes do not ionize. One solute molecule dissolved results in just one particle, so their ionization factor is just 1. Ionic compounds and strong acids are strong electrolytes. We can determine the ionization factor by counting the ions in the chemical formula. For example, calcium hydroxide contains 1 calcium ion and 2 hydroxide ions, giving a total of 3 ions. So I is equal to 3. Sodium phosphate contains 3 sodium ions and 1 phosphate ion, giving 4 total ions. So I is equal to 4. Once the ionization factor is known, compounds can be ranked by freezing point or boiling point. More particles leads to a higher boiling point and a lower freezing point. On a thermometer diagram, boiling point increases as the ionization factor increases above the pure solvent, while the freezing point decreases as the ionization factor increases below the pure solvent. Consider this practice problem. Predict the ionization factor for each compound. Sodium sulfate is an ionic compound and therefore is a strong electrolyte. It forms 2 sodium ions and 1 sulfate ion, giving a total of 3 ions. Hydrofluoric acid is a weak acid and therefore is a weak electrolyte. It has an ionization factor between 1 and 2. Ammonium nitrate is an ionic compound and dissociates into one ammonium ion and one nitrate ion, giving a total of 2 ions. Calcium hydroxide dissociates, giving one calcium ion and 2 hydroxide ions, giving a total of 3 ions. Finally, C3H6O is a molecular compound composed of only nonmetals, so it is a non-electrolyte with an ionization factor of 1. Now let's rank solutions by boiling point. We have a 0.5 molar sodium chloride solution, a 0.5 molar magnesium chloride solution, and a 0.5 molar C3H6O solution. Although the listed concentrations are the same, the ionization changes the effective particle concentration. Sodium chloride dissociates into 2 ions, magnesium chloride into 3 ions, and C3H6O does not ionize. Because boiling point increases with the number of particles, C3H6O has the lowest boiling point, followed by sodium chloride, and MgCl2 has the highest boiling point. Osmotic pressure is another colligative property. Osmosis is the flow of solvent from a less concentrated solution to a more concentrated solution through a semi-permeable membrane that allows solvent but not solute to pass. Consider a container divided by a semi-permeable membrane with pure water on one side and a sucrose solution on the other. Water flows from the pure solvent side into the sucrose solution. This decreases the liquid level on the pure water side and increases it on the solution side. Flow continues until the pressure exerted by the height difference stops further movement. This opposing pressure is called the osmotic pressure, and the more concentrated solution has the greater osmotic pressure. Here is a practice problem. A semi-permeable membrane separates a 10% starch solution, A, from a 5% starch solution, B. Let's draw a picture to help us see what's going on. Solution A is more concentrated, so solvent flows from B to A. As solvent moves, the solution volume A increases while the volume of solution B decreases. Therefore, solution A has the greater osmotic pressure. Water initially flows from B into A, and the liquid level of solution B becomes lower. Osmosis also occurs across cell membranes and affects blood cells. An isotonic solution has the same osmotic pressure as a blood cell, so there is no net solvent movement. In a hypotonic solution, the surrounding solution has a lower osmotic pressure, causing water to flow into the cell. In a hypertonic solution, the surrounding solution has a higher osmotic pressure, causing water to leave the cell, resulting in cell shrinkage or crenation.